What's an example of actually, you can probably give me 3 or 4 examples of real numbers that are not rational.
Like pi.
Pi.
Root 2.
Root 2.
E.
And
any square root that's not the square root of a perfect square is...
Right, square root of n and not a perfect square.
Yeah.
Is irrational. This actually you know how to prove, right? You know how to prove that the square root of 2 is not rational.
Yes.
E, actually, you probably don't know how to prove, but that's fine. But there's a proof that actually you could understand. Pi is a lot harder, believe it or not. Proving pi is irrational. Actually, I forget when that happened, if it was in the 1800s or maybe... I think it was in the 1800s. The pi was proved to be irrational. So actually pi being irrational was a little hard, but there are definitely numbers that are not rational. We know that for sure. And so it's a very natural question, having said, hey, if I look at a number line from 0 to 1, and I fill in all the rational numbers, it certainly looks like I've filled in basically everything.
Except for a few points.
There's a few holes, but I can't, as I mentioned yesterday, there's no interval that doesn't have a rational number in it. So it really does, and that's why they're called dense. So they sort of fill in everything except for some holes here and there. So the natural question to ask is, well, okay, what about the real numbers? If there's essentially the same number of rational numbers as integers, maybe there's the same number of real numbers as integers. And it turns out that there are more real numbers. It's a higher infinity.
Yeah.
And I don't know, probably I've shown you this proof before, but do you remember it?
Yeah. I think it's a little bit different than the previous proofs, but so I think you basically start by assuming that they're the same size and you sort of predict that.
So assume you have a list.
You've created the one-to-one mapping.
Okay, and then we may as well just stick to 0 to 1 again, just because it's easy enough to do. So I'm going to have all my numbers 1, 2, 3, 4, 0.1234, 5, x, 0.29174, x, 0.71896, etc.
Yep.
And this is where 1 goes, this is where 2 goes, this is where 3 goes, 4 goes, there.
So you've created that rule.
Okay, so I've created the rule. Okay.
And then what you do is you create a new irrational number that doesn't fit with any rational numbers because it's for positive integers, because it's different than any of the previous irrational numbers. So...
Yeah, well, I do want to, just be slightly careful. These are just numbers. They're not necessarily rational or irrational. They're just all the real numbers from 0 to 1. Okay. So we don't know if they're rational or irrational. They certainly could be rational. It could be sort of like 0.3000000 forever.
Okay.
Okay? But okay, so what do I do now?
So you take the first digit of the first number you have here, and you change it so 1 could become a 2.
Okay.
Then the second digit of the second, so the 9 could become a 0. The third digit of the third, the 8 could become a 9, and you go down the line and you create a new number that, because you've changed all of the digits in it, it's different from all of the previous numbers.
Yeah, it differs from every number in your list in at least one digit.
Yeah.
And so then I now have a new number. Let's just call it 0.9421, etc. And you can say, you told me you listed out all the numbers, but I just found one that's not on your list.
And so that won't align to any positive integers.
Okay. So what's the problem now?
Well, you can do this infinitely many times. So now you have a larger infinity, because you can't you've proven that there are more elements in this than in this in some sense.
Yeah, almost. Let's go to the last video here, and then we'll finish up.